record, and I'm going to make that disappear. Okay, so we've got this Minimax folder over here. I'm going to encourage you to take a look at this. And what I want to do right now is just talk about like Minimax and what Minimax actually is. I don't know if you've actually heard the term Minimax. Are you familiar with this? Something. So it's a concept that you maybe are not like entirely unfamiliar with. I like to think of it this way. So the idea, as a preamble, I don't know if you've ever played a game against a friend, or maybe you are this friend who takes like forever to take a move. And you're like, what are you thinking of? And they're like, well, if you play there, then I'm gonna play there, and then I'm gonna play there, and I'm gonna play there, and you're gonna play there, and I'm gonna play there, and we're gonna and they do that, but the problem is they're not doing that for like one move, they're doing that for like all of the moves, right? Like every single possible case in every single possible condition. And it's nice when they can do this quickly. It's like less nice when it takes 15 minutes to get a turn out of them. This is my dad in Scrabble. I'm like, Dad, you just have to play. You have to pick something. You have to do it. And it's my sister-in-law and other guys. But you know what? It's everybody to a certain extent. That's part of strategy, right? It's part of that is part of strategy. We all do this a little bit. And we do this not just with games, but we do this in other things too, right? Like there's a test coming up. Oh, I know I'm not going to do well, so I'm going to take the retake. So we start doing like, how am I going to do the retake? When's that retake going to be? When's the best place to take? Oh, but maybe I should take the physics retake instead because that's going to be on this day. And then we just kind of you play the scenario out in all of its possible manifestations. In a sense, this is what the Minimax algorithm is doing. Okay, the idea behind Minimax is that we're going to be choosing our move based off of the notion that our opponent is going to be choosing the best possible move for themselves at every possible node of this tree. We're going to choose the best move for ourselves that gives our opponent the worst possible outcome. Like I'm gonna put myself on the path where you playing your best way gives you the lowest possible score, right? Like I'm gonna choose the move which guarantees the lowest possible outcome for you, assuming you're playing most strategically all along the way. So what does that mean I have to do? Go say it. You have to minimize. I have to minimize the other score. I have to maximize my score. There's a lot we have to do. Yeah.
I was thinking it's like similar to BFS or whatever, like through all problems.
You have to do that. These two together is the answer. You have to loop through that entire. You're like looping through that entire tree, playing that out in every single case. They'll play here, they'll play there, and they'll play there and there. But they could also do this. But we could also take a step back. They could be here versus here versus here. And if we can do this systematically and collapse all this information back to the source, we'll know what's the most strategic move for us. We'll know the move. We can choose a move which is like going to guarantee us better results. And we can learn to avoid moves that are going to give us like horrible results. Does that make somewhat of sense? So the algorithm that we're going to use is somewhat generic, and I'm giving you code to do this. Okay. I think it's beneficial for us to have this code. What I want to do today is work through this code a little bit, and I have it on the Zoom so you can see this. But at the same time, I want you guys to use this code for yourselves and play with it, because as much as it is beneficial for me to describe this to you and for you to sit and nod along and look with it, you kind of have to make it and break it and work it for yourself too. That's sort of necessary. So I have what begins over here. We're going to start this with tic-tac-toe. Okay, we're going to do Minimax with tic-tac-toe. And the reason we're going to do this with tic-tac-toe first is to kind of get this notion. Do we all know how to play tic-tac-toe? That's the question first. Do we begin with do you know how to play tic? Yes. Okay. So, and there's a reason why we're starting with tic-tac-toe first, as opposed to other sorts of games, in Othello. Let's kind of just go through here. So I have this, let's go here. And this will be recorded. So you can
get a sense of this. So what I've got first is a representation of a game board, right? So we should be somewhat familiar with this notation over here, where if I say dot, 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 xxx, dot, 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 that's representing this 2D board that's going to look like this, right? And if I have something that looks like boom, 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 this is OXO, ba, 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 over here. I'm representing these boards as 1D strings, and I'm printing them out in 2D using the trick that I've talked about before, using this comprehension over here. So for X in the range of 3, I'm printing the slice that corresponds to each row. This is just so you can see the representation, and we can sort of see over here the various patterns. So if I have the first, the second, and the third, or the 3, 4, 5, 6, 7, 8, 9. I don't think I can really count right now. But if we get these rows, slices, verticals, and diagonals, there are a set of terminal conditions where the game can be won or lost. So how do you think we're going to solve this? What is a great way of going through every single possibility, doing everything over and over? Yes, recursion. It is our friend recursion. I do not know how you do this without recursion. Okay, we're gonna be doing recursion. And I know that within Fellow, some of us have been sort of avoiding recursion a little bit, and figuring out those, looking outwards for moves. I don't know how you do this without recursion. Recursion is the right answer for this, okay? The idea behind recursion, we've done this before now so many times over. The first thing we have to do is we identify some base case. Right? The base case, that terminal condition. So in tic-tac-toe, the terminal condition is going to be having a slice of the board match either OOO or XXX, or not finding any dots in that. Why not finding any dots in that? What's this last one? It's a tie. Right? So tic-tac-toe, we often get ties. So what I have here are 9 different splices, and credit to Dr. Gabor on this code. This is like adapted from my interpretation as well, but we have this terminal triples. If we have some function over here, I have a board, I'm going to have some token over here. If this is it, O wins, X wins, or others. So in deciding what our terminal conditions over here, we're starting with minimax, and I'll talk about the difference between minimax and negamax in a moment over here. But I have these 3 different sort of things that we could possibly return. I could return something that has a -1, a 1, or 0. So the notion behind minimax is that we kind of pick this perspective of either X or O, white or black in chess, white or black in Othello, player 1, player 2. There's going to be one player who aims to get the most positive score, and the other strives to get the most negative score. So here we have O trying to get the most negative score, and X trying to get the most positive score, right? So we have a singular the singular representation when we get this -1. So what we have this thing set up, my recursive algorithm over here, I have this staged for terminal conditions where it can say, hey, you know, if I found, sorry, if I have this XXX in the string somewhere, if that is a proper terminal condition, this is going to return a dictionary that has a 1 in it. This is going to return that dictionary with a 1. This is a case of O winning. This is a case of O winning. And this is a case of tie. And this is a case of an incomplete board. So the reason why we're returning this dictionary that has either it's empty or just a -1 is a little bit subtle. And I'm going to encourage you to play around with this. But the idea is that we're kind of looking to see at the next layer on, we're going to say, hey, run the minimax. And if you wound up getting some key that had a -1 inside of it, if you return something that had a -1 in it, then that means O is going to win. If you had something that has a 1 in it, that means X is going to win that. And so the idea is we're setting this up so that we have this board, and we're going to be calling this on all these possible different terminal conditions
And we're gonna be pulling back and we're gonna be asking ourselves, do any of these have this key inside of it? One, positive one. Is this a bad or a good?
So we'll get, I don't think I did the best job of explaining that. We'll get into that in 1 second. But the base point here is that this is either returning a dictionary that has a -1, 1, or 0 based off of the possible moves. Next thing, get moves. We need to be able to get the moves out of a board, right? You need to be able to find which are our possible moves. In this case, finding a possible moves is as simple as saying, hey, these are the indices that have a dot in them. Okay, so for my second function over here in get moves, I say here, this is my board 1. What are going to be the get moves of board 1? What do you think? Should just be say it again. Yep, 0, 1, 2, 8, 7, 6. And it's going to give me it gives me a list. So I get this list of possible 6, 7, 8 also works. It's not necessarily ordered. We're getting this list of the possible indices. Okay, so this code is working. It's saying, hey, at each stage of this thing, we're going to be getting the moves.
And what do you think we're gonna be doing with these moves once we've got these moves? Yeah. Hey, so we analyze them, figure out which has the highest score. How do we analyze them? What do you think we need to do with these moves? What do we need to do with these indices? What do we need to do next? I have 6 different possibilities over here. So I have 6 different places where I could play. Now, granted, these are sort of silly conditions, but 6 different places where I could play. I'm going to go through and I'm going to stick my piece in this guy. And I'm going to test out and say, what's this? And then for the next move on, we're going to stick the other piece, the O, in that next condition, and each this thing out, build that tree down, 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 and ask the question, hey, do we have the terminal condition? All the way down. Fill it out with this piece. Test it for 0, then test the next, then test the next, then test the next, then test the next. We're going to try all of these cases. So it's kind of an exhaustive algorithm. Here I have no moves, and here I have a move of 8. Okay, great. The next thing, make a move. So in this case, my make a move is actually quite straightforward. I just take the board and I build a new string, right? Take the board, put the token that's supposed to play, and put it in the right place over here. And so here, if I say if I take my board, if I make this move at X at 0, at X at 1, at O at 0, it's just a string substitution. I'll leave it to you guys to go through that and take a look at that. That's straightforward. The next question over here for number 4 is, okay, well, we need to kind of do this in a loop, right? If we're going to be doing this, testing out the entire span, the entire tree of possibilities of this guy. I have some board, I have some token that's going to be playing. So for each of these moves, right? So for this move, which is an index, for every index and getting all the possible moves, I'm going to be making a new board here. So in the 4th one, here we go, right? So this is kind of the way that we're beginning over here. So I have some piece. I have all these possibilities. I'm going to be testing my algorithm on each of these guys. And then each of these are going to get passed into that algorithm again, and it's going to recursively go through and test X filling in at all the different places. And then O is going to get filled in. So we have like tens of thousands, if not hundreds of thousands of millions of different possibilities that are going to get evaluated inside of this. Questions?
Sorry, I don't quite understand why it displays like that. Why
Excellent question. Why is it displaying like this? So what I have over here is I have my board that I started with. So I'm starting with this is not the original base condition over here. If I were to make this, right, like the default condition, basically for this in get moves. So get moves of the board is going to be a list that has 0 through 8. For this in get moves, I make a new make move is going to construct a new string representation with O. It's just doing a string substitution at each place along the way. So here, so in this case, I just substituted O in at each of the possibilities. But if we had something that looks like this, it's going to substitute an O at each of these possibilities along the way. So that's all I'm doing. I'm using this as a board constructor for each of the cases. Good question. Okay, so we've got board constructor inside of here. So the idea is that knowing that I have some board, right? This game is happening. Maybe X played here first and then O played here and then X played here. We have no real sense of what the actual like to hide that. We have no real sense of what the order was that brought us to this place. We just know that this is what the board looks like right now. And knowing that the board looks like this right now, and knowing that it's going to be O's turn, I'm going to get a list of each of these possible places over here. What we're looking to do basically is say, okay, build a new board. I can print this new board. And then I'm going to be asking this question because this is kind of how that recursive works, right? We ask if we're in terminal conditions, we construct the new state, and then we pass that into that algorithm again, right? That's this recursive. Did we reach the terminal condition, generate a list of possibilities, and then pass those guys into our algorithm again and go down and down the line. So we're preparing this guy and preparing this guy to go into that recursive algorithm here. So just for you to kind of look at this, I want you to see point is point right here. The point is that right now these are all returning none, right? So in this case, these are all returning none, but I'm showing you that I can construct a board. My algorithm is going to be construct a board for each possible case and throw it into the minimax move. So where is this going to be going? Construct a new board and throw it back into minimax. Where is that going? Where does this belong? He's going to go right. Going to be basically like in my recursive algorithm. We can begin to see like this is kind of what we're building up towards, right? So my recursive algorithm is going to be something along the lines of, hey, here's my minimax. Here's this terminal condition. Either we're going to hit the terminal condition because X is 1 or O is 1 or we're out of moves. Then if we're here because the game is not yet over, right? We're here because the game is not yet over. And because the game is not yet over, I'm going to start creating new boards and passing those new boards into my recursive algorithm. That's where we're going with this. And then each of these new boards is going to be passed back into this algorithm. And the first question that's going to ask is like, hey, is this a win or a loss or a draw? If it's not a win, a loss, or a draw, I'm going to take and I'm going to run this algorithm again. I'm going to construct a new board and I'm going to run it again. Now, what am I not doing when I'm demonstrating this right here? What am I not doing? There's a subtle game. We said minimax was the opponent was playing the best possible. So here we have to figure out some way of getting the opponent to play the best move. Opponent to get the best move, opponent to get the best move. Let's go here. So this other one is just this is just demonstrating these terminal. This is just demonstrating that I can, if it finds, so this algorithm, the way this thing passing a board that looks like these strings is either going to return a none in this case because I haven't finished filling out my algorithm yet, or if it hits this condition, if it hits a terminal condition, we get the thing that says either terminal condition for O in this case, or none, or I didn't put an X winning condition inside of here. But we're getting something different if passing this through returns a terminal condition for either X winning, O winning, or running out of spaces. That's what I'm trying to show here. Tearing right along. By number 7, I actually have my Minimax algorithm like live and in person right here. Okay. So this is a helper function. This thing I put in dprint. You don't need to use this or understand this or know this. Basically, what it's going to do is it prints out each key and value in an dictionary on separate lines. I have a way of advancing the token, so getting the next token. So for example, if the token is X, I return O, else return O. So this is flip-flopping my tokens over here, right? Whosever turn it is, I pass it to this, I get the next turn. We know what get moves is doing. We know what make move is doing. It's making a new string. I feel like we're at the point where I can start talking to you about what this Minimax is actually doing. That was the preamble. Welcome to Minimax. So the deal now with Minimax is that I have some terminal state. I have some conditions that can be found, and I have some resulting dictionary that this thing is going to throw back at us or not. I can get the next player's move. So I know how I got called into this thing, right? It's either a blank board, maybe with turn to X. We substitute in X in all these positions. And for each step along the way, I put X in, and then I throw it back into Minimax. When I'm in Minimax, I need to say, hey, okay, now it's O's turn. And O has to pick the best move that's best for itself. So O's going to pick a good move. And then O's going to pick a good move. And then it's going to Minimax that. And then X is going to play a move after that. And X is going to pick its best move. And then, or sorry, it's just going to pick the next move on that tree. And we're going to go down all of these trees and basically building up all of these nodes until we find the terminal conditions that lie at the end of them, right? It's either going to be -1, 1, or 0. If, assuming that the player is playing strategically best all along the way, we get a -1, we say, okay, that's a channel. If you can find any -1s at all in there. So basically I'm saying, hey, if the turn is, I make a new board, I get the opponent's result, right? I advance the token. I get the opponent's result by going through and running their Minimax on this thing. If the token were X, what I'm going to say is the best that O can do over here, I'm returning up that minimum value out of here. So if there was a -1 inside of there, I'm assuming that O played that -1, right? If the choice was between X winning as a +1 or 0 for draw, I'm assuming that O chooses to play the lowest possible. O chooses a 0 over 1 because that's a draw versus an X win. And O chooses -1 over 0 because that's an O win over draw. Okay. So O is looking at this and it's saying, hey, whatever I got over in here, whatever the values that came out of this dictionary that we got back in those terminal trees, in all the terminal nodes down inside of there, if there was the lowest possible one, that is the one that I am choosing to go to. Okay. Similarly, or that is the one that I was choosing to go to. Similarly, if we're O, we're assuming that X is picking the max. X is going to choose a draw over an O win. X is going to pick a +1 over a 0. X is going to pick an X win over a draw. right? So the idea behind this dictionary is we're looking at the values that came out of this guy. We're looking at the values, and this last thing right here, this is not keyed to any particular index. It's just a value in that dictionary. If there is a 1 in the dictionary of those terminal trees, X is picking it over the alternatives. So this becomes really, really cool, right? So let's take a look at this. So I have on 0.7, excuse me, 0.7, maximizing 0.1. Now, I want you to pay attention to something that just did over here. So this is subtle. This is a working minimax over here. I'm going to clear the screen out. I have a halfway decent computer. What did you notice about that? Was that answer? Oh, yes. Right. Yeah, it takes time because I'm copying. And how many different possibilities am I figuring out along this way? Like 9? Am I doing this 9 times? Like, no. Doing 9 times 8 times 7. I'm doing this like 9 factorial different combinations. I'm making 9 factorial dictionaries and copies of strings along the way. So that took a while to figure out. And in the end, I just got a whole set of zeros. What does this even mean? What do all those zeros mean? What is that telling me? Yes. It's a draw. If you're playing optimally, like it's a draw. Tic-tac-toe is a draw. If you both know how to play tic-tac-toe, it's a draw. Great. And that's actually the answer. Yeah. If you know how to make the optimal move, it's a draw. The secret is tricking people into making less than optimal moves. So let's make this a little bit interesting over here. So for this number 2, so this is the same thing. Oh, and the point here, you can see my dprint. This is my dprint function. So the reason I dictionary print is I just have a little comprehension that prints the key and the value, key and the value. That's what dprint is here when you guys play this on your own. I think this is a little bit more readable. Okay, so here we go. Second one. He's a thinker. Oh, wait a minute. Did I change that around? Oh, yeah. So for X, whether it's X or O starting. Oh, I guess that's the thing. Whether X or O starts. So intuitively, that may not be the right answer. But I have the third one, and this is maybe not the best situation. This is not really realistic, right? Like if there's a single X on the board and it's turned to X, what do you think this is going to tell us? What do you think my minimax is going to? What's that? X wins. Yeah, this is X wins. There is no way O does anything here, right? So if X is in the middle and X gets a second turn to start this game off, there is literally no way that O gets to beat them. I'm sorry. So I think that was number 3. I don't even know why I did that. But the point of this is that we have some code that we can begin playing around with. And over here is where I start to get this a little bit interesting. So let's take a look at this board right here. So I don't know if you can see this super well, and I'll draw over it. I have O, X, nothing, X, O. Did that show up? That made it worse. That definitely made it worse. O, X, X, O. Okay. So this is presumably a game that could have happened. So if it's X's turn at this point, what I'm going to do is I'm going to pass this through the minimax, and I'm going to quit it out. And our results are over here. So this is where we start to get interesting. So here I have 2 is -1, 3 is 0, 5 is 0. What is this telling me? Read these results and tell me what this is telling me. Yeah. So which spot is my loss over here? It's saying if I play here, and O plays optimally, that there's no way X can win. Intuitively, does this make any sense? So I'll have us do this. Let's say this. If I have O, X, then if X plays here, where's O going to play? The bottom. O plays there. X or X is now, X does not win this game, right? So X can stave off defeat a little bit longer if it plays any place. If it plays here, it's done. If it plays in other spots, it might be able to prevent that win from happening. So that's what this algorithm is telling me right now. When I ran that first time through right here, this here, O is going to win it. Tie. And we can see this. The cool thing about this is that you can actually begin to see this actually happening, right? So we put the X right there, and O says, okay, let's see what this gets now. So I ran it 2 through, and here, so the first time through is like, yeah, this is X's turn. If O plays right here, we get a -1. And then once O is played in that 6th spot, that game is over. I substituted in 6. The key here to note about this, with this minimax, is that what we're sort of assuming in this situation. So you're going to see here, I've got 3, 5, and 8 are 1s, right? A 3, a 5, and an 8 are X win conditions. So what do we have? 0, help. So slow. So if I play here, here, or here, if I play in any one of these 3 spots, X wins this game. But there just has to be one -1 in that tree for the minimax to say O is going to pick that position. Does that make sense? So the minimax that generated this -1 for that spot at the level before was the minimum value among all of these possibilities. So when the tree was collapsed, when these trees are collapsed upwards to generate that first thing with those, because we start off with, however many 9 factorial possibilities, but the tree is going to be collapsed all the way through. And the minimum value is going to be chosen. And that's what we're going with at the end. Yes, Ron. That's, well, depending on which player you are, right? So if it's X's turn, X is gonna be like, oh yeah, X is gonna aim for that highest value, and O is trying for that lowest possible value. And we're always assuming that. And so you have this like competitive alternating decision as you work your way back up that tree, and we're keeping track of it. This is a good question.
So for a function, we're just assuming that chooses the optimal.
That is it. We're always assuming this opponent chooses the optimal moves, because there are definitely non-optimal moves that the opponent could have chosen here. We evaluate based off of the opponent choosing the optimal move. Yes.
Is there some sort of like support having like a more probabilistic evaluation? Like, let's say the more possibilities, like the less foreseen your opponent can make, the more possibilities they can mess up when you find something.
So this is kind of a very like binary decision that we have over here. But in a proper implementation, absolutely. You could add some probabilistic element into this and be like, oh, they're more likely to choose this one. So maybe the decision kind of varies a little bit. And we also have this thing where, you know, tic-tac-toe is very deterministic. We can look at this, it's very easy to figure out. There are other games where it's not gonna be that straightforward. We don't necessarily know. And if you think of Othello, like, what is it that you're trying to get? Are you just trying to get the most amount of moves? Are you trying to get the most pieces? Are you trying to get the best locations? So you begin to develop this heuristic of like, what is it that they're actually gonna be going for? What is the most probabilistic thing that they're gonna be going for? And your simulation of your opponent's best guess is only as good as your brain, right? Like, is only as good as your algorithm can come up with. So when I'm choosing what my Othello minimax is gonna look like, if I'm just choosing randomly, the best I can do is assume that my opponent is choosing randomly. If my best guess at it is the little box around here, then that's the best approximation that I can assume for my opponent as well. So the craft of this, once you have that working system that says X wins, O wins, X wins, O wins, blah, 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 is coming up with like, what is a better algorithm? What is the one that gives you better results out of this? So you have to, does that make sense? I'm getting some nods, but I'm not getting total nods out of you.
Okay, geez, we're almost done. So tell me something. So, okay. When I ran this for tic-tac-toe, think of how long that took. Tell me about Othello. Tell me about your friend Othello.
Is that gonna work for Othello? No, why not? Yes,
It's such a big role.
it's a big board. Are we really gonna evaluate 64 plays and expect this thing to just to get a whole set of O's coming out at the end? Right? So when do we do this? When are we gonna be doing mini packs? When do you think? Yes, Nish. Close to the end. We'll start doing our mini max once we get close to the end. So we'll start developing this different strategies at the beginning versus at the end. How do we identify if we're at the beginning of the game? How would we do that? Yes. Number of dots, right? We can count the number of dots. We can say, hey, if it's in the beginning of the game, try to grab the fewest number of pieces. If it's at the end of the game, we'll run this minimax thing. If it's in the middle of the game, maybe we'll like avoid this section or something like that. Like you can begin to count the number of pieces and actually craft a personality for the way that your thing is going to be playing this game. Yes.
Instead of how do we say only one word change? Now function like.
Absolutely. So we have done optimizations in this class along the way. I feel like this worked well for demonstrative purposes. Like if speed is your goal, then you're gonna need to start thinking about these small changes to get you. Yes, absolutely. There's no question.
And so yeah. And then finally over here, I think I made another, was it 05? I made this 05. So you can look at this and play around with these things. This code is here for you to look at. And there's no question that I want you to like look at this and evaluate it. And I'm saying like, I put some questions on Schoology. Ask yourself the question, like, why are we doing this? Why am I using recursion for this? What's the benefit for doing recursion? Here we've got another board. I mean, this is basically the same as the other. All right. So,
Does anybody feel comfortable enough to describe what minimax is right now? Feel like shouting it out, scream to the sky. What is minimax?
You're just digging from two perspectives of the game and trying to get the best possible values on
Okay. We're trying to get the best possible game tree based off of of any loop. You assume your opponent is trying to win. We've got positive values for one team, negative values for the other. You look at those and make a decision. So, turns out that's actually not what we're going to be doing for Othello. We're going to be doing something called Negamax and Negamax. And Negamax is basically Minimax. It's a form of Minimax. But we can kind of assume a slightly different perspective out of this, where instead of assuming the positive and the negative, we can just basically take the absolute value of this, so to speak. And we have a slightly different goal in mind, where we can, instead of trying one being optimizing and the other, so one maximizing and the other minimizing, we have it so that both players are maximizing their own score. So with like a small modification, you configure the algorithm such that each player is maximizing their own score with the strategy. It's really more of a bookkeeping nuance than anything else. It's the same thing, whereas instead of one trying to get as high as possible, the other getting as low, they're both trying to get high, assuming we can represent it that way. So what I have over here, I have is Negamax. This is going to be a little bit different. I'm not going to lie. This looks differently. And I encourage you to look at this. So we have a lot of things that look similar, right? So I have a way of advancing the token. As you pointed out, this is less than optimized. I have my dprint over here. This is not exactly super fast. I have my next token. I can get moves. I can make a move. And I have Negamax. What I'd like to show you just off the top right here is what this looks like over here. So I'm going to say Python 08 negamax.py. Oh, you're a thinker. The idea here behind our Negamax output, we're going to be looking at a slightly different representation of this as well. We're going to kind of invert the representation where I have the win case, the lose case, the draw case, and it's going to be dictionary, and the where keys are like win, lose, draw, and the values are going to be some set that corresponds to the indices that I could play that will lead to that particular condition. The reason why this is nice and is extensible is because what we can do with Negamax is we can kind of have multiple keys. Like this is going to be the move that gets us 11 flips. This will be the move that gets us 10 flips. This will be a 5 flip move. It gives us much more freedom in the choices, right? These are, instead of just trying to get the highest, we can say, oh, maybe this is like the highest number of flips, or this is the highest number of corners. We can look for different conditions. We can organize this differently categorically to define what we're looking to get out of here. And this becomes the set of things that we're trying to get out of here. So what I have over here is this is my board, right? This is my Negamax. I'll do a quick substitution in here, and I encourage you to play around with this code and try to understand it. So here I've got my 08 Negamax. Here, okay, right? We saw this again with substituting X in the middle over here. Right? Like what if I do this though? O has that, then we have something more interesting. Like you can configure board conditions and get the expected outcomes for an X. If I start playing here, win, lose, draw, win, lose, draw. This works a little bit differently, and I just want to guide you through. We've got 5 minutes before lunch over here. I want to just guide you through, and this is for recording, so you can kind of see what this is. We have my terminal triples over here, right? So these are the same sort of conditions. I've got my board and whoever's token is. I'm going to figure out what my opponent's token is. And I kind of look and say, hey, if I've got my opponent's token, ... in one of these terminal triples, I'm returning this dictionary that says, like, for this base case, right? For this terminal case, up. For my terminal case down here, if I have found my opponent 3 times in the terminal triples,
this is going to key true on loss. Else, I've got some set over here. And so what we're going to begin to have at this terminal condition is this set that we're defining at these terminal nodes, and this set is going to be propagated upwards, right? So this set will be passed upwards along the way, and we can sort of envision that as it's collected and aggregated at each step along the way, as we retract backwards out of our recursion, we'll analyze this through and say, hey, which places got you that loss? Which nodes were hitting that win? Which nodes were hitting the draw? And the best one, of course, expected output. So if it's a draw, we start that terminal, right? So if we draw, and so as a sort of visualization, right? So we had boom, 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 all these different trees down here. We're starting with a dictionary because we hit all of those conditions. We start with some dictionary, and that dictionary is going to be propagated upwards. And that dictionary for this node down here begins with win being empty, draw being empty, and loss being true. And if it happened that the board filled out with none of these, and we didn't hit those opponent's terminal conditions, we started with the win being empty, the draw being true, and the loss being an empty set. And as we go to the next layer up, we're going to aggregate these guys together. And how do we do this? So we say, okay, here, this is some set. Propagating upwards, we do the same kind of thing. We got the moves, we look at the move, we do the negamax on this thing, and we say, hey, if in the negamax for that next board through, if negamax of win was found, right? So negamax of win, if negamax of W, if that were true, right? If the negamax of that next layer down had a true on the win, and lose, basically this is saying if you wind up getting either like the win, I'm backwardsing out of my brain out of this thing. So if the negamax of the next, because it's the opponent's, right? Yes. So if the opponent wins, you get to see a loss in that column. If the opponent draws on their next play, that becomes a D. If or else, it becomes a win. So, right? So if the opponent wins, that means we lose because we're negamaxing on the opponent's token. We're negamaxing on the opponent's token. And we just add to the set and propagate upwards. What I really want you guys to do, and it is out of time, we're clearly out of time. It was only an hour today, got to go to lunch. What I want you to do is to take a look at this, try to play around with this. This is going to be the basis. You can basically take this code and begin to work it into Othello. Okay, this negamax is going to be the basis for Othello. It's not necessarily something to submit. It's more like tell me that you play around with this and think about why we would use recursion. You should have an answer in your head to why we would use recursion. You should have an answer to your head of what does this return case look like as it propagates upward through these things. What does that dictionary look like as it gets built out, as that set gets built out? And you should be able to construct that because you're going to need to be able to construct that. I'm going to stop recording. Thank you for now. I hope that was somewhat interesting. Is this isn't even recording anymore, is it? Oh, wait, it is. Here we go. So